Hi everyone, welcome back. In this video, I wanted to make a tutorial on the theory of SAR reconstruction for 3D radar imaging. So I think from here on, sort of this becomes more interesting and more close to my own research. So, I'll be able to hopefully make better videos from now on this series. Okay, so this is the fourth sort of video. What we will discuss today is 3D image reconstruction for synthetic aperture radar, which is also known as SAR. Okay, so that's the title of today's presentation. So I will divide this sort of into two parts or three parts, depending on how long it takes. So in part one, we will look at the generalized signal model. So this for FMCW, step frequency, and pulsed radars. So what I want to do here is basically to form a generalized signal model, which will allow us to do SAR reconstruction for any kind of radar. It doesn't matter if you use FMCW, step frequency, or pulse radars. So I'll do that in the start. And then part two, once we have the signal model, then we will discuss reconstruction algorithms. So we will discuss back projection, or sometimes it's called back propagation. BP for short. Delay and sum. Yes. Time domain correlation. TDC. And I would say actually 3D match filtering. So my goal with this video is to really show that once we have a generalized signal model, all of these four algorithms are in fact the same. They're just different names for the same thing. So I'll just put that in bracket. They are all the same. So some of them are in frequency domain, some of them in time domain, but mathematically they are equivalent once you have a generalized signal model. Okay. So then in part three, which I think I'll do as a separate video, depending on how long this one takes. So in part three, I will show you MATLAB code for reconstruction. This is with like synthetic targets. So let's say I just make up a target of some point targets. And then I'll show you HFSS to MATLAB. So basically, if I have, let's say, some random target, I can download a 3D model of a tank or a plane or a hidden weapon like a gun. And then I'll show you how to simulate SAR data in HFSS. I actually have already a video on this, which I did for a class that I was TAing, teaching assistant for. So you can check it out. It's on my channel. But I'll do this again for FMCW. So in that case, I did it for sort of step frequency radars. So if you want to look at that, you can look at that, but I'll repeat it for FMCW, which is different. So that will be useful. And then thirdly, the most exciting one is to use experimental data. So I've set up some experiments for part of my research really. And we'll use that data, correct that data, and correct as in like calibrate that data, and then use MATLAB to reconstruct images. So it'd be nice to see what experimental data looks like. So this will be part 3. Okay, so that's sort of the plan. With that, let's move on to part 1, which I will call 4.1. Okay, so as usual, we start with some intuition. This is basically the intuition behind SAR and SAR reconstruction. So what is synthetic aperture radar? Right, so the idea is that typically for imaging, you may use a lens to focus the image, but the idea behind synthetic aperture radar is that you can take a single antenna, single radar element. So let's say I have a single antenna here, and I have some target. This is my target, let's say. What I can do is I can illuminate this target from this antenna or radar, and then collect the backscattered data, and then move this target, move the radar. So I'll move it from here to here, and then collect the data again. Then again, move it here, collect data, move it here, collect data, and so on. So I do that over, let's say, a raster scan, right? So then now I have this backscattered data or my radar data over a 2D plane. And you can use anything, you can use FMCW, step frequency, anything, it doesn't matter. So once you've collected this data sort of over this 2D plane, then the idea is to reconstruct what this target looks like from this collected backscattered data. And the neat thing about SAR is that it has many advantages. So one advantage is that it is essentially like using a lens that is of this size, which can be much larger than any physical lens that you have. The second interesting thing is that you can focus the image in 3D. So a lens, for example, will either focus at a single imaging plane. So maybe this is your imaging plane. And then, if I have a lens that is this big, it would focus here. The spot would be around lambda over 2. And then the spot diverges after that. Or you can even focus at infinity when the target is very far away. But you cannot focus in a 3D space. And the third thing is that you only need a single antenna really, right? So it's unlike phased arrays where you need many antennas, you need to control the phase. Here the reconstruction is done in the signal processing side at the end. So these are sort of the advantages of synthetic aperture radar. Another thing actually is that the angular resolution or the lateral resolution and range resolution are independent of position, which is again a huge advantage, right? So whether you're close to the array or far away from the array, your resolution is still the same up to a point. So beyond a point, when you go very, very far away from the array, then your resolution starts to drop. But sort of up to some extent, the resolution is the same. I won't go into too much detail of SAR now. We'll discuss this at a later video, why that's the case when I talk about the resolution. But that's the idea behind SAR anyways. Right? So what is the intuition behind reconstruction now that we have some idea of what SAR is? Okay, so the intuition behind reconstruction is sort of like this. So let's say I have, a point somewhere here that I'm interested in, and I have another distinct point somewhere here, right? So you see that from this element, let's say I have another element here, just arbitrarily choosing these elements. So these 3 elements illuminate this point, and they also illuminate this point, right? And the idea is that when you look at, say, the black point from all of these elements, the signal that you receive overall is different than when you look at, the purple element, right? So because the signals are different when you look at from all these different angles of arrival or angles, and also over a large frequency band, the signal, the backscattered signal from different points is different. And the basic idea of SAR is that using some signal processing tricks, you can reconstruct a good estimate of what this target looks like based on the difference of these signals. So obviously we'll work out the mathematical details, but that's sort of the intuition, right? So this is the synthetic aperture. That's why it's called synthetic aperture, because you don't really move. You just move the single target. You don't have many elements. Actually, one subtle advantage of SAR over phase arrays and reflector arrays, things like that, is that you don't have any mutual coupling, right? Which is, for those of you who know about this, mutual coupling between elements can make focusing really difficult. But in SAR, since you only have one element, it's a synthetic array, you don't have any mutual coupling issues. So that's something to maybe keep in mind. Okay. So now that, we've developed that sort of intuition, hopefully, we can move on to the generalized signal model. So in the previous 3 videos, we talked about the signal model for FMCW, for step frequency, and for pulse radars. But that was only for like a single radar over a bandwidth. Here we want to look at the 3D signal model, right? And we want to generalize it for all 3 of them so that we can treat all 3 radar systems the same: FMCW, stepped, and pulsed. Okay, so let's do that. So if I have an antenna, let's say this is the phase center of my antenna. So phase center is sort of the point on the antenna. It's sort of a fictitious point from where spherical waves emanate. So, at the far field of your antenna, the waves are of the form, the phases of the form e to the ikr. And this is essentially a spherical wave. So the center of that sphere, of those spheres, basically is the phase center. I'm not going to go into details of phase center. That requires another video, basically. So let's assume you know what a phase center is. So I will, in some coordinate system, let's say this is my coordinate system. Let me call this Z. Let's say this would be X and this would be Y. Okay, so in this coordinate system, I will call this point R prime, which is given by X prime, Y primes in Cartesian coordinates. And then let's say some target point I'll label as XYZ or R, vector R, which means that now this vector is R minus R prime, right? So, basic vector calculus, this is R prime, this is R. And let's call the length of this R minus R prime vector as R minus R prime, which from geometry you can show is just X minus X prime squared plus Y minus Y prime squared plus Z minus Z prime squared. Great. Okay. So first we'll deal with FMCW 4.2.1. So I'm not going to review the basics of FMCW again. I've already done that. So we'll just start with the IF signal that we receive. So let's say I have some target at a distance R, single target. So the single target IF signal looks like this, which is already covered in the other video. So if the distance between the radar and the target is R, this R, then the IF signal was shown to be 2 omega C R over C plus 2 beta RT over C minus 2 beta R square over C square, right? And we said that, okay, this is the residual video phase term. This is the center frequency of your chirp. This is the chirp rate. and t belongs to minus ts over 2 to ts over 2, where ts is the chirp duration, c is the speed of light. Okay. Now, one thing you can do is you can just ignore the residual video phase. And we discussed in that video as well how important it really is for close range targets. But okay, let's say you cannot ignore it. Then in fact, you can actually remove the residual video phase. And I won't go into this now. When we discuss another video in the future, just because of time constraints, I'll show you how you can remove it. That actually requires a separate video. So I might make a separate short video on how to remove residual video phase. If you're really keen and you want to do it right away, then you can look at Carrara and Goodman, the book. And in the appendix, they cover how to remove the residual video phase term. Okay, so let's assume we can remove that for now. And for simplicity, I'm also going to use convert cosine to a complex exponential. Okay, now you really do this. In some FMCW systems, they do have actually INQ signals, so you can have a complex signal. But if you don't have that, if you just have a real signal, just have the cosine term, this is still okay. So one thing you can do is you can go to Fourier domain and then remove the negative frequencies and come back. So that's like a synthetic way of getting an exponential out of a cosine. Or you can actually just use your real data and assume it is complex exponential. If you do that, what would happen is that your unambiguous range would become half, but you would still be able to reconstruct the signal. So I'll leave that as an exercise. So what does this really do? This assumption that, okay, even if my actual measured signal is real, but I treat it as a complex signal, what happens? If you think about it, it's pretty simple. It actually doesn't do anything wrong, anything bad. Okay, so with these two assumptions, I can say that, my beat signal for a target at a distance r from the system is simply exponential of minus j times 2 omega c over c plus 2 beta t over c times r. Okay, I'll make a substitution. I'll say kt is equal to 2 omega c over c plus 2 beta t over c. And with this substitution, it's pretty clear that, my signal model now for a single target is simply e to the minus 2 j, maybe I should say e to the minus j 2 kt r, which is very nice. It's a nice expression, I guess. So this is the IF signal or the beat signal. Okay. Next we deal with, so here I said 4.2.1 is FMCW. So we've generalized FMCW to this expression. So then we saw, okay, step frequency, what was the signal model? So this would, I think, be 4.2.2. Step frequency. Okay. So we saw that in step frequency radars, my TX signal is e to the j omega t, and my RX signal is e to the j omega t minus 2 kr, right? Where k was omega over c. And then you can basically just divide the two. So then SB of R for step frequency would just be the RX over TX, which is just S11 if you're using a network analyzer. Or, it could also be S21 if you have a separate TX and RX, depending on how you set it up. So that is simply E the minus J 2KR, right? So you see that's now it's in the same form as the FMCW signal. So then SB of R is equal to e to the minus j 2kr. Okay. And the last kind, which is pulsed radars, 4.2.3, pulsed. So we again developed this in the previous video. So we said that TX signal is some pulse, P of t. I don't know what it is. And then the RX signal is simply P of t minus 2R over C. And then we showed that after match filtering, the match filtering response is modulus P of omega square times e to the minus 2j kr, where this is the Fourier transform of this signal. So we can kind of ignore this amplitude term. We'll justify that later, but you can, let's say, ignore this amplitude term because it doesn't change much with frequency. In fact, it doesn't really, even if it does change a little bit with frequency, it doesn't affect the image reconstruction. So with that assumption, I can again write SB of R is simply just e to the minus 2j kr. So ignoring this amplitude term, I will justify in a few minutes. So just bear with me for now, right? So from all this, we can conclude that basically, therefore, the generalized signal model can be written as SB, which is a function of R, right, where the target is, comma. It's also a function of where the location of your element is, and it is a function of K, right, is equal to e to the minus 2j. I'll just write K. K is equal to KT for FMCW, mod R minus R. Okay, so this K is KT for FMCW, so it's a time domain thing for FMCW, whereas for step frequency and pulse radar, it is simply K, which is omega over C. Okay. Write this. So KT, which is equal to omega C plus beta T over C. And this is simply K, which is omega over C for pulsed and step frequency. Okay. All right. So one thing, if you remember that we did when we developed all these signal models, is that we excluded the propagation loss, right? So we said, okay, if you really have a radar system and a target at some point, what you have is a spherical wave that goes out and it scatters off of this and comes back, right? So really, SB, if you want to be a little bit more precise, SB of R should really be e to the minus 2j kr over r squared, right? Because you have 1 over r going one way and then 1 over r coming the other way. And that's why you have the 2. It's actually just e to the minus j kr over r, which is the forward going wave, times e to the minus j kr over r. Right? That's why you have the factor of 2 here in the phase and a factor of 2 here in the amplitude, because signal goes one way as a spherical wave, scatters and comes back as a spherical wave. And for the EM experts out there, this is the Hankel function, right? The spherical Hankel function of the first kind, which is the solution for spherical waves. Okay. So we'll use this for now, and we'll see working with this, how does it look? This is somewhat a little bit more accurate, right? Considering the R square, we'll make it a little bit more accurate and sort of work with what is the best at the end. Okay. So the next section, which should be, I think, 4.3. So these were the three signal model. This was a simplified signal model, generalized signal model for the single target case. So if I have, let's say, a 3D target, 3D signal model, right? So then basically I have my array here. I have some 3D target. Let's say this is X, Y, Z. Again, R is just R minus R prime. So we saw that, okay, we are SB term. And let's say at some point, the reflectivity function, earlier we assumed it's 1, but now it's not going to be 1 because it changes as a function of position. So we'll define more precisely what exactly do I mean by this, but let's just say, okay, the reflectivity at some point is given by some function as a function of the location of that point, which I can also write as f of r, right? So then my measured signal for that point is simply given by f of r times minus the phase modulus of r minus r prime over r minus r prime squared, right? So this is the single target signal model. And now since target, different points have different reflectivities, so we include that in here. So the actual measured signal that you measure at the antenna, at some antenna which is located at r prime, and you're measuring at k, which for FMCW is a function of time, the IF signal is a function of time, and for pulse and step frequency is a function of frequency. This is in fact approximately the integral over r. So for all points, there's reflection basically from, so, this point contributes, this point contributes, this point contributes, all these points of the target contribute to your measured signal. Right? So you have to integrate, all of those add up essentially. F of r e to the minus 2 jk mod r minus r prime over mod r minus r prime square dr vector. I'm saying approximately because, of course, there is noise and things like that, which I haven't included in this model. So this is sort of a simplified model. So expanding that out, it is integral over xyz, f of xyz, e to the minus 2 jk square root of x minus x prime squared plus y minus y prime squared plus z minus z prime, I guess you can say, but I've assumed that z prime is 0. So let's assume you set up your coordinate system such that z prime is, or you can include it, that's fine. But moving on, we'll set z prime to be 0. Whole divided by x minus x prime square plus y minus y prime square plus z minus z prime square dx dy dz. Okay, so that's the actual measured signal. So now we'll refine this model a little bit just to get a better intuition as to what's happening. So we've made some assumptions here. I want to clarify this moving forward so that if you want to improve on the model and it's just important to keep in mind what assumptions we've made. So the first assumption is that the antenna is omnidirectional, right? Assume it's a spherical wave equally emanating in all directions. So that's an assumption. Second, here we assume that the target is a contiguous collection of point scatterers, right? And we've ignored multiple scattering in some sense. So we said, okay, every point on the target scatters a spherical wave, and you can write the target as an integral over all of these points. And, 2 points that are next to each other, they don't scatter waves between them. So for example, if I have one target here, one target here, we assume the wave comes here and this goes back, comes here and then goes back. But in reality, I mean, it could hit this, and come back. It could, hit this and bounce many times between them and come back. So you sort of ignored all of those cases, right? Okay, so the next assumption is that we ignored dispersion effects. Version of channel and, that includes system. So there's dispersion in the system. In, for example, the residual video phase that we've ignored for FMCW. And also channel dispersion, which is also somewhat important. So what do I mean by that? So in the system, the phase is not necessarily linear with frequency, right? Ideally, phase should be omega t plus kr, right? But because you have amplifiers, antennas, filters, so on and so forth, for wideband systems, this is not necessarily always exactly true. So dealing with this dispersion is a separate problem. I'll address that in a future video, how you can correct for example, residual video phase, dispersion effects in the system. And your channel can also have dispersion. This is more rare, I would say. So for example, if it's raining or if it's foggy, that can introduce some channel errors. And that's much harder to model. For now, we'll just ignore it. Keep it simple. Okay. Then we have ignored target scattering as a function of frequency. Right? So we assume that, okay, my target also has no dispersion, and that is also not true. So for example, if I have a target with some concave structures, which have some resonances of their own, then, your target will not have a backscatter that is linear with frequency. A phase of the backscatter wouldn't be linear with frequency. Yeah. I mean, for example, you can look at the scattering response of a sphere as a function of frequency. It's called the Mie scattering solution. So that's necessarily not always linear, right? You have the creeping wave, and for different frequencies, the backscatter can get canceled. So you may not have a linear response with frequency. That all of that we've sort of ignored. Okay. And then one more thing that we've ignored is we've ignored the wavelength dependence on received power. It's a little bit more subtle, but basically the received power of an antenna is a function of wavelength. It's not independent of wavelength. We'll discuss this a little bit now. So these are sort of the assumptions that we've made. It's important to keep them in mind. So, okay, the second part, which is target as a continuous collection of point scatterers. I mean, this is somewhat true at millimeter wave, at least especially for real world targets. So I'm not going to go into that much. This we will address later, how to correct for system nonlinearities. Also, this I'm going to ignore. I'm assuming that, okay, this is valid, which is again somewhat true for real world targets, rough surfaces, things like that. About 0.1 and 5, we can actually correct them pretty easily. And I'll just do that for the sake of completeness now. Okay. So keep losing track of what the section number is. Okay. 4.4, which is more accurate. Signal model. Maybe that's not a good title because it's very long, but who cares? Okay. Zoom in. All right. So what we want to correct is we want to develop a more accurate signal model. And I'm just doing that for the sake of completeness again. So for this, we'll go back to the radar equation and derive it, essentially. Okay, so if I have, my transmitting antenna here, and the target is out there, once again, this distance is r, then the first thing is that the target has to be in the far field of your antenna. Only then this phase center approximation is valid. Keep in mind that it doesn't mean that the target has to be in the far field of your synthetic aperture. Right? Synthetic aperture is much larger than just the single antenna size. So you have to be in the far field of the antenna, but you don't have to be in the far field of the synthetic aperture. Okay, so we know that in the far field of the antenna, the power density is, let's say PD, is the transmitted power, amount of power transmitted by the antenna, times the gain of the antenna, we'll call it GT, or let's just assume it's G, divided by 4 pi r squared, right? That's basic antenna theory, I guess. Okay, so that's how much is the power density that reaches this target, right? Now we know that the power reflected at the target is given by the power density that arrives at the target times the radar cross section, sigma. That's really the definition of the radar cross section, is the reflected power over the incident power density, right? Okay. So that's the amount of power that's now coming back this way. So now again, we go back and do what we did at the first step. So we say, okay, then what is the power density at the receiver? Power density at the receiver is, again, same trick. You have some power that was radiated, and then you have to multiply that with the 1/4 pi r squared, right? Because that's power radiated is divided over an entire sphere. Okay. Then power received. Now that's the power density at the receivers, and the power received at the receiver is simply the power density times the effective area. Oh, I call this GT again. So let's see GT. Okay. GT sigma A E, which is the effective area of your antenna, 4 pi r square whole square. And effective area is defined as, in terms of the gain, which we call GT, is lambda square GT over 4 pi. Right? So substituting that into this, so then the power received over the power transmitted for a radar system is GT square lambda square sigma over 4 pi cubed r to the 4. Okay. And sigma can also be written as 4 pi modulus of s square, where S is the ratio of the scattered field over the incident field at the target, and it's called the scattering amplitude. Okay, so this is the power, and we know that the ratio of power, square root of the ratio of power is the ratio of the electric field. So the received electric field over the transmitted electric field can simply be given as ratio of PR over PT times e to the minus 2j kr. So it's sort of a heuristic derivation. It's not an accurate derivation. So this is the phase term. Obviously, power doesn't have phase. And the square root of the power ratio is the electric field ratio. So that is essentially lambda g, which is the gain of your antenna, which is actually a function of the direction, r hat, times the scattering amplitude, which is the function of the position, divided by 4 pi r square e to the minus 2j kr. So effectively, our SB should now be written as a more accurate estimate of SB, more accurate model as a function of r prime and k. So if we go back, so we had this integral, right? So I want to rewrite this integral, to say what exactly is this f in terms of the scattering amplitude of your target, right? So this would be better to write it like this. So this was your, your small SB, right? Now S tilde B, which is the integral over SB, is simply integral over x, y, z, lambda g of r hat. R hat is basically the direction of r minus r prime. S of r over 4 pi r square e. This 4 pi. I'll also include a term L here. I'll explain what that is. Times e to the minus 2j kr over r square dx dy dz. So this L here is the loss in the system. So, we've considered all the losses in the channel, but the system itself has some loss, right? And that's a function of frequency, to be more precise. This is a much more accurate, signal model, right? So this essentially is your f of x, y, z. Right, so now we have, a representation of what is f of x, y, z in terms of the scattering amplitude, right? Okay, and although we derived this more accurate signal model, it really doesn't help much when you're trying to do a reconstruction. Right, so in terms of just imaging, unless you want to be very precise and reconstruct exactly the scattering amplitude of your target, for synthetic aperture, this gain, you can assume, we've assumed, in fact, you can assume for synthetic aperture, the gain is actually low. It's not that, it doesn't change much with the direction, because in fact, for SAR, you want an antenna that has a very broad beam. We'll talk about why that is maybe in the future, but essentially, if you have a very broad beam, then your target is illuminated by every element, right? So if I have a broad beam, then this target is illuminated by every element. And that's why this assumption is okay, that the gain is sort of independent of R, right? Okay, so for simplicity, we'll just use the simplified model. SB tilde of x prime, y prime, k is equal to, for imaging, this is good enough, of x, y, z. e to the minus 2j kr over r square dx dy dz. Sometimes you can actually also include this r square in here, right? Because even r doesn't change much. Even if it does change, your targets will just become, your image will be dimmer and dimmer as you move away from the target if you plot the final image. Whereas if you account for r square, then that sort of accounts for that. But in some simplified models, they may even consider just f of xyz times e to the minus 2j kr. Right? And depending on the situation, we may use either one. Okay. So really the goal of radar imaging / reconstruction algorithms is to reproduce f of xyz from SB tilde, the measured signal f of x prime y prime k, as accurately and quickly, say also efficiently as possible. Okay, so hopefully that should be clear now. We have this integral, and what we want to do is to invert this integral to go from this to this. So this is what we've measured, right? So we measured the response of the backscattered fields at all these points at different frequencies at different times. And we want to reconstruct the target response. Okay, so let's look at some algorithms that can do that. So maybe let's use a new page for this. Sorry, I just need to go back and look at again the section number. Okay, 4.5. Let's use black. Reconstruction. Finally, we're getting to some imaging. Okay. So here we will use back projection, back propagation, whatever you want to call it, delay and sum, which are essentially the same thing. And we'll also look at time domain correlation, / match filtering in 3D. So usually in the literature, these are for, this name is used for pulsed step frequency radars, and it's a frequency domain technique. Whereas this is used for FMCW radars. And this is a time domain technique. So despite these differences, really, since we've developed our generalized signal model, the simplified version or whatever, even the regular generalized signal model, the reconstruction turns out to be mathematically identical for all of these. So when we use the 2J KTR or KR, Okay, so let's see what that is. So we'll start by the frequency domain version, frequency domain. So this is 4.5.1. So you can think of this as frequency domain back projection or delay and sum imaging for pulsed and step frequency radars. Okay. So again, I'll give you some intuition and then we'll do the math. Right. So what is the intuition? So let's assume, for sake of argument, I have 3 antennas. And we said that, okay, I have, let's say one target here and another target out here. So let's say this is some undesired target. I don't want to image this point. Undesired pixel, I'll call it. And this is my desired pixel or desired point at which I want to create the image. Right. So, okay, from this radar, signal goes out, it's red. So we have one signal that goes and comes back. From this antenna location, it goes and comes back. Do that again. And then from this, it goes and comes back. Also, you have the same thing to this target, right? Goes and comes back, goes and comes back, goes and comes back. Okay. So I'll label these. So I'll call this, R1A. That's the distance to the first one. R2A and R3A. That's a two-way distance. Okay. So the two-way distance here is R1B, R2B, and R3B, where this is B, this is A, and let's say this is 1, 2, 3. Just for the sake of simplicity, that's the labeling I'm going to use. So now what we'll do to develop intuition is we'll use the phasor model. So if you don't know what the phasor model is, I would highly recommend go back and look at the video on step frequency radars. Okay, so sorry, let's put this correctly. So that's one phasor. So that's my, my complex plane. So we said that, okay, for R1, as it goes and comes back, it accumulates, starts from here, and then goes around, let's say, as it propagates, hits the target somewhere, let's say here, and then again propagates back, and then ends up somewhere here, okay? So in that case, I'll denote it like that. So just for simplicity, I'm going to remove all this circle. So I'll say, okay, after the two-way propagation, the phasor ends up somewhere here, right? So yeah, that's number one. For antenna 1 to the, so I'll say this is for the desired pixel, right? And then for element number 2, actually, erase this and say, okay, it ends up here, let's see, right? So this is your element number 1. Now for element number 2, it may end up somewhere here, right? And then for element number 3, let's say it ends up somewhere here. Okay. Now what you want to do is when you reconstruct, if you want to focus on this pixel, you want to bring all of these back to 0, right? So you want to unwrap them again. So you want to bring that back, you want to bring this back, and you want to bring this one back, right? So we know that if the location of the two-way phase was R1A, the two-way distance was R1A, and the phase that the first element sees for that pixel was e to the minus j, or let's say R1A is the one-way distance for simplicity, that would be minus 2jk R1A. This one is e to the minus 2jk R2A, and this one is e to the minus 2jk R3A, right? So to unwrap it, the first one has to be multiplied with e to the 2jk R1A. That undoes that will undo this phase, right? Because the minus and plus cancel. Some space there. Okay, so let's do this again. So this guy, to unwrap, it needs to be e to the 2jk R1A. This guy needs to be e to the 2jk R2A. And this guy needs e to the 2jk r3a, right? So you're basically unwrapping it after it got wrapped. But this unwrapping process is also applied to this pixel, because these two are essentially, you can't separate the two signals, right? You receive all the signals at the same time. So what happens when the unwrapping is applied to the undesired pixel? Let's look at that just as an example. Illustration, right? Okay, so the wrapped phase from the undesired pixel to the three antennas, maybe it ends up, the first guy ends up there. So this is number one. Second guy ends up here. Third guy ends up here, right? But now each of them is going to have, so this one would be e to the minus 2jk r1b. This is e to the minus 2jk r1 r2b. And this is e to the minus 2jk r2 3b, right? But now you're unwrapping each one by not the r1b, r2b, and r3b, but r1a, r2a, and r3a. So this one may come back somewhere here instead of coming back all the way to 0, right? So for argument's sake, let's say this guy comes back here. This guy, the 2 may come back there, and the 3 may come back here. So this guy comes back there, this guy comes back here. So now, okay. So now what happens when you add them? So let's say I take this one, the unwrapped version of this, plus this one, which is the unwrapped version of this, plus this one, which is the unwrapped version of this. When I add these three signals, now I end up with this response, this vector, right? Whereas here, when I was adding them, they were all three in line. They would basically, it kind of went outside the page, but yeah, this one, and then how do I draw this? I'll just draw it as small thing. So, the three of them lined up, right? So when you unwrapped them and added them up, they all lined up and they added coherently. So this is a coherent addition, right? Whereas here, when you unwrap them, they didn't come back to 0 because you're not unwrapping for this point, you're unwrapping for the point A. And because of that, they don't add up coherently. So this is incoherent. Right? And that's sort of the idea, is that for the desired pixel, when you do an unwrapping, all the signals add up coherently. Whereas for all the undesired pixels, they don't add up coherently. They go all over the place, right? So essentially, this is, once you understand this picture of what's going on, that's the entire basis of coherent imaging, right? So for the desired pixel, if phase is unwrapped, or I would say actually when the phase is unwrapped rather than if. Phase is unwrapped and added, or when phase is unwrapped, coherent addition of order n to the 3 phasors occurs, right? Because essentially you have, what do I mean by n to the 3? So I have, n by n elements, let's say, n by n elements, and I have n samples in time or frequency, just for the sake of argument, time or frequency. Right, so that is essentially my SB tilde of x prime, y prime, k. So this is n, and this is n. So I have a 3D matrix, right? And I'm taking all these 3D I have a 3D matrix of complex numbers, and each complex number is a phasor, right? So when I coherently add them at a single pixel, you get n cubed. N cubed signals add up, they line up like that, right? So it's a lot. And then you add them all up, so you get a very strong signal. Whereas at another undesired point, it's very hard to exactly line up n cube pixels. I mean, it may go all over the place, right? And then at the end, you'll end up, when you add them all up, you end up with that. Whereas here, when you add them all up, you end up with a very strong signal. So this is coherent, and this is incoherent. And this order n cube multiplication factor that comes is called the processing gain of SAR, right? Because although you went and hit the target and came back and you had some amplitude, now you get a gain of n cubed because the amplitude of all of these signals is adding up at that point, right? So this is somewhat not fully understood by some people, I think, because they say, okay, SAR doesn't give you as much signal to noise as a lens-based imaging. In fact, it gives you more. It is almost like using a lens that's as big as the SAR. So that's the processing gain. So intuitively from this picture, you can get an intuition of what is actually going on. So let's say I have, my desired pixel here. Okay, so we saw that, okay, when I add the signal here, it's very strong, right? Because my target is here and I'm looking at this pixel. But let's say my target is here and I'm looking at the pixel next to it. Then what happens? Then you may get, signals that don't exactly fully cancel, but maybe they start veering away a little bit, right? So then your vector would be like this long, right? So you look at the amplitude of that vector, it would be this much. So you don't fully coherently add, but they don't completely cancel because very close to your actual array, right? So it doesn't fully unwrap, but unwrapping is not bad. And then you go a little bit further away, it'll be that much, and then that much, and then that much. And at some point it fully cancels. And in fact, again, it'll start adding up a little bit, and then again canceling, and so on, and then it becomes zero. When you're far away from this pixel, then everything completely cancels. So this is an azimuth, right? In range, it's the same story. So you have in frequency, because remember that this unwrapping is also happening in frequency, right? So when you unwrap in frequency, at this point, all of the signals unwrap properly. But then if you're somewhere close by, they don't unwrap exactly right. And then again, it's the same thing in range. Right? And we covered this also in the step frequency video. So if it's a little bit confusing, you can look at it there as to how it happens in range, but it's the same idea. So when you actually look at the envelope of this whole thing, it may look something like this. So this is an azimuth or lateral. In direction. And you can say, okay, this is in range. It's sort of the same thing. Looks something like this. So what this is showing is that even though my target is only here, it looks like as if it's sort of smeared out in this direction and this direction, right? It is not exactly a single point because coherent addition happens even outside the target, outside that point. So this smearing or spreading occurs of the target. And that's what is called, so this function, which shows what the target looks like is called the point spread function. PSF. This is a very, very important concept in imaging. So the point spread function is only a function of your imaging system. It is target independent. It basically tells you if I have a single point target, what does the image look like of that target? And once you know the point spread function, you can know everything about your system. You know what the range resolution is, azimuthal resolution is, what the dynamic range is, so on and so forth. So knowing the point spread function gives you everything you need to know about the system. So your final image, in fact, you can show is a convolution of the point spread function and your target response f of x, y, z. I won't go into too much of that now, but that's sort of the intuition behind point spread function. Okay, So now that you have a good intuition of what this frequency-based reconstruction is, let's look at the math, right? Sorry. Okay. So again, I need to look at 4.5. Okay. I'll just call it math. Okay. So we have SB tilde, X prime, Y prime, K, right? So for a pixel at R, you want to multiply this. So for a pixel at R, which is XYZ, you want to multiply this. To unwrap it, we need to multiply X prime, Y prime, K with the opposite phase for that pixel, right? 2j K modulus of R minus R prime. And once you unwrap, we saw that, okay, once the unwrapping is done, then all you need to do is add up all those tiny vectors that are unwrapped, right? So that is an integration or a summation. Sum over X prime, Y prime, and K, right? So now, and this is again the n cube, right? So all those n cube vectors are all lined up. So now all you want to do is sum it up, right? And that is essentially the reconstructed target response at the pixel XYZ. It is summation over K, summation over X prime, summation over Y prime of SB of X prime, Y prime, K times E XP J 2K square root of X minus X prime square plus Y minus Y prime square plus Z minus Z prime square, but let's say Z prime is 0 plus Z square. Okay. Essentially that's it. So that's how you reconstruct. You take your signal, which is a 3D matrix. You form this steering matrix, they call it. I don't like that term because that comes from like 2D steering. Here, you're not really steering. You can call this the compensation matrix or reconstruction matrix. So this is also a 3D matrix because it has X prime, Y prime, and Z prime. So this is your steering matrix. You multiply that, and then you sum over all of those 3D elements. So you do a sum in MATLAB. Or sum, once you form this multiplication, you just do that, right? And that gives you at a single pixel XYZ, right? So you do this at all pixels of your interest, and that will give you your image. That's it. The amplitude of this function is the image. So this is sort of the complex image. And you take the amplitude, and that's the image that you can display. So from this, it should be clear why it's called back projection or delay and sum, right? Essentially, you're projecting back all the phase that you picked up, or you're delaying and then adding it up, right? So that's why that's the name. So this is the frequency domain version. To get a different intuition in time domain for FMCW, we'll do that more quickly. That's a little simpler. So that is 4.5.2, I believe. Sorry, I keep losing track. 3, okay. So this is correlation in time. It's a different kind of way of looking at this. Okay, so this is simpler, I think, to understand, but mathematically, again, I have my 3 antennas. I have, let's say, 2 targets, A and B. So it's 1, 2, 3. So, okay, I have for target A, so for target A, I have some signal that goes through all these 3. So that gives me, my single target matrix, right? 3D matrix. This gives me another single target 3D matrix. Let's call that SBB. So the signal that you receive for target for point A and for point B is different, of course, right? Because you're looking at it from different directions at different frequencies and so on. So these two are not equal if A and B are quite different, right? So what the idea here is that since SB tilde is a collection of all of these target responses, you want to see, okay, how similar is the actual signal that you receive to SB of A. So obviously, if you have only a point target, these would be exactly the same, right? Whereas if you have a collection of all of these, how similar is your measured signal to an ideal signal that comes from this point target? So we do a correlation. Correlation of SB tilde with SBA, that is the signal from the pixel of interest. Right? Okay, so now we know that SBA of R is f of R over R square e to the minus 2j kr, right? For simplicity, we say, okay, we ignore this R square because it doesn't really matter, only the phase matters. You ignore this. And obviously, we don't know what this is because that's what we're trying to figure out. So we say, okay, that's 1. So let's assume if I had a target at some point, then that signal that I would receive would be just e to the minus 2j kr. Right? And if I have two signals, then the correlation between the signals, C of tau, this is sort of known, is if the signals are complex, then I need to take the complex conjugate of one of them, dt, right? So that's the definition of correlation. So here I have two signals. I have my SB tilde and SBA, and I want to find the correlation between them, right? So at my desired pixel of interest, f tilde of R is given by the correlation between SB tilde, which is the measured signal. So this is a symbol for convolution, SBA conjugate. So when I take the complex conjugate, that becomes correlation. No, my bad. So this is correlation. So you take correlation between this and the estimated signal at pixel R. Right? So that tells you how similar is basically the measured signal to the signal that you estimate from this pixel, right? And we know that this is simply just the integral over x prime, y prime k, SB tilde of R, comma k, with e to the 2j k r, right? Because it's the complex conjugate of this. And this is essentially exactly the same now. The discrete version of this is what? F tilde of x, y, z is approximately, of course, sigma, 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 a, x prime, y prime, SB tilde of x prime, y prime, k times exp times exp of 2j k square root of x minus x prime square plus y minus y prime square plus z square. That's it. So essentially, we've shown that time domain correlation and back projection have the same mathematical expression. once you have the right signal model, right? Okay, so that's why this is called time domain correlation, because this K is in time domain, it's time domain signal. So essentially just a correlation. And match filtering, if you watch the video on match filtering that I did for pulse radars, you'll also notice that match filtering is essentially just a correlation. So this is a 3D match filtering, right? So therefore, zoom in for emphasis with the generalized signal model, back projection, delay and sum, time domain correlation, match filtering are all mathematically equivalent, or identical even, I would say. That's great. So that completes, I guess, the mathematical derivation and the intuition behind these algorithms for reconstruction. Before we move on, I would actually like to spend some time to discuss. I know it's getting kind of long, but I think it's worth it. For those of you who are still watching, I guess. So what is the computation time of back projection slash time domain correlation, right? So assume we have an imaging scene that has n cross n cross n pixels. And for the sake of simplicity, we have n by n array and n frequency or time samples, right? So we saw that for each pixel, we have n cube multiplication and summations, right? So that's n cube multiplications. Or flops, I suppose, if you want to get really technical, right? And we have n cube pixels as well. So implies that computational burden of these algorithms is on the order of n to the 6th, right? Because it's n cubed for each pixel, you have n cube pixels. So total for 3D imaging, that's n to the 6th. That is actually very slow. It's too high. Why is it too high? N is, let's say, 100 by 100, which is not much, right? So I'm just looking at 100 by 100 points. I have 100 by 100 elements. 10 to the 2 implies I have to do 10 to the 12 computations. And this number grows very fast with n, right? So for large scenes, for high resolution 3D imaging, this is not practical. It's still a good algorithm, I think. It's the most basic kind of reconstruction. So let's discuss the advantages and limitations of these algorithms. Or should I say this algorithm? This is, I don't know, 4 point something. I'm just not going to go back anymore to look. Okay. So you can actually show that time domain correlation gives you the highest signal to noise ratio because it's match filtering essentially. Another big advantage is you can use any arbitrary geometry. Of the array, right? We haven't made any assumption that it should be square or it should be rectangular, circular, doesn't matter. You can use any position for your elements. and you can still reconstruct. Something a little bit more cool or more subtle is you can image on any arbitrary domain of your image, right? So if I want to, at any arbitrary pixel, I can form an image. Of course, it doesn't mean that if you make, you form images on pixels that are very close, you get very high resolution. The resolution is determined by the point spread function, right? And we'll talk a little bit more about what the resolution in cross range and range is when we talk about the next set of algorithms. I don't want to get into it now because it would get too long, but essentially, even if you form pixels that are very close, it is the point spread function that determines the resolution, not the pixels you choose. So you should be judicious in choosing pixels. You don't have to choose 100 pixels for a single lobe of your point spread function, for example. But you can make it arbitrary. You can do any cut, any domain, curved surfaces, whatever you want, right? Of course, the big limitation is that it's very slow. And it requires a lot of memory as well, right? So depending, if you do for loops, it's slow. If you use vectorization, it requires a lot of memory. So the big question now is the final question, with which I will conclude this tutorial, is can we make it faster? Right? So it's great. You can reconstruct very nice images. You can see through walls. You can see through the ground. You can do all kinds of cool stuff with this millimeter wave SAR imaging. But what's the point if it's so slow? If it takes you hours or days to form an image, it's not good, right? And the answer is yes, you can. So the intuition behind that is that we had this triple summation of SB R prime e to the 2jkr, right? Now, if you think about it, this looks awfully similar to cube SB R prime e to the j kxx plus kyy plus kzz, right? And that is what? That is k dot r, the dot product of the k vector and the r vector. Here you're just multiplying the magnitude, so it's not exactly the same, right? So you have this sort of this k dot r, which is kr, cosine theta, when theta is the angle between these two vectors, right? If you only had this, we only have this, but we don't have this part, right? So if you could write it as k dot r, this triple summation, that would be very nice, because this is essentially just a Fourier transform, right? So your f tilde would then be the Fourier transform of this, but we don't have that. We have it in this sort of kr term, not the k dot r term. But so to speed it up, what we need to do is we need to express this as this. And the key insight is that this is a spherical wave, whereas this is a plane wave. So essentially we lose a spherical to plane wave expansion to express one as the other, and then we can use Fourier transforms. So if you can do a 3D Fourier transform instead of all of this summation and everything, then the order of computation would be reduced from n to the 6 to order n cube log n cube, which is actually much, much, much faster, especially when you're using large arrays and for very high resolution imaging. And this is the basis behind algorithms like range migration, frequency domain omega k, holographic reconstruction, etc., etc. All of them are essentially the same thing, again, with different names, because different people came up with it, I guess, in different applications, but they're all the same. And even I have done some work in doing time domain holographic reconstruction for FMCW 3D imaging, and I'll present that in a subsequent video. So this sort of motivates why these algorithms exist. It's just to speed up the process. But you have to place some restrictions, so you will lose this capability to some extent. Maybe a little bit here, maybe not. We'll see. So you kind of trade off your arbitrariness to get fast reconstruction. right? We'll discuss that in the next future videos. So just to give you a heads up of what's coming next. So the next thing would be the MATLAB demonstration, HFSS demonstration, and actual experiments and measurements. So we'll deal with experimental data. And I'll obviously provide all these codes, including the HFSS example, and also even experimental data so you can work with it yourself. Okay, with that, I would like to conclude. Hopefully this was not too long for those of you who have actually stuck around till the end. Hopefully you enjoyed that. So thank you so much. Have a nice day.